In the last lecture, we studied that a coordinate basis can be used to represent points and vectors. In this lecture, we will see how to represent a second basis in terms of the first basis. How can we relate A and B, where A and B are two coordinate bases? We can assume that one coordinate basis is represented by the V vectors and the other coordinate basis is represented by the U vectors. Each of the basis vectors u1, u2 and u3 are vectors that can be represented in terms of the first set of basis vector, that is the V's. We can write this in equation form as u1 is equal to gamma 11 v1, gamma 12 v2, gamma 13 v3. Similarly, we can write u2 and u3, and this relationship holds for some values of gamma 11 to gamma 33. We will find how to calculate these values. Okay, let us represent u1 in terms of the basis vectors v1, v2, v3 first. So u1 is equal to gamma 11 v1, gamma 12 v2 and gamma 13 v3. Note that v1, v2 and v3, these are vectors. So this is a vector, this is a vector, and this is a vector, and they're basically column vectors, and this makes this first term as a matrix, and this is a column vector. So in matrix multiplication, a row from the first matrix gets multiplied with a column of the second to produce one term, and because we have vectors here placed as column vectors to make a matrix, we can write that as a matrix V, where V is basically the matrix of the coordinate vectors of the V basis. Now similarly, we can write an equation for U2 and one for U3 and convert them to matrix form like this. So U2 is a product of the matrix of basis vectors V multiplied by these weight vectors, which are different from the previous weight vectors, because the previous weight vectors have subscripts 1 1, 1 2, 1 3. This one has 2 1, 2 2, 2 3. The 2 basically refers that we are calculating the second basis vector of this new coordinate basis, and we do a similar operation for U3, where V is again the matrix of the V coordinate. We can write all the coefficients gamma in the form of a matrix M, where the coefficients associated with U1 form the first row, U2 forms the second row, and U3 forms the third row. And we can write the coordinate system U in terms of the coordinate system V as U1, U2, U3 is equal to V multiplied by M transpose. This sign is for the transpose of a matrix. And in matrix form, you can write U is equal to V M transpose. Notice that when taking transpose, this will become the first column of the M transpose matrix, representing the coefficients of the U1 vector. We can have the same vector W represented in the two coordinate system. Now this W is the same W. If we represent it in the coordinate system defined with V vectors, we have the alpha 1, alpha 2 and alpha 3 weights. If we define the same vector W in the coordinates represented by U vectors, we will have different set of weights. We call them betas, beta 1, beta 2 and beta 3. We can write this in matrix form as V1, V2, V3, which is the vector or which is the matrix of coordinate basis V multiplied by alpha weights, which gives us the matrix V multiplied by the weights alphas, and we call that vector as A. Now similarly, we can have the U basis in matrix form defined as capital U and multiplied with the weights beta, which we denote with B. Now this is the same vector that we can represent in the two different coordinate bases. Now we have two representations of the same vector W. One is in the v coordinate basis and one is in the u coordinate basis. Because this is the same vector, we can relate these two representations as VA is equal to UB. Since UB and VA are both equal to W, we can write as VA is equal to UB. Recall that we have already established a relationship between the two coordinate bases V and U. They are related with M transpose. So if we multiply V with M transpose, we get the coordinate frame U. Hence, we can replace U over here with VM transpose from this equation. And this will give us a similar term on the right hand side and the left hand side, which we can cross out. So V can be crossed out from both sides and we'll end up with A is equal to M transpose B. Thus A and B are related by M transpose. Note that this is a pre-multiplication as opposed to post-multiplication here. So we can conclude that the matrix that takes the coordinate basis V to the coordinate basis U can also take the representation of a vector in one coordinate basis to the other. We can apply a similar process in homogeneous coordinates to the representations of both points and vectors. Consider two coordinate frames, one represented by the point P0 and vectors V1, V2, V3, and the other coordinate basis represented by the point Q0 and the vectors U1, U2, U3. So these are two coordinate bases. We can represent one coordinate basis in homogeneous form with respect to another coordinate basis. The same set of transformation will apply here. Any point or vector can be represented in either coordinate frame. We can also represent one coordinate basis in the other coordinate basis. We can extend what we did for the change of coordinate basis to points. So representing the basis vectors of U bases in terms of V bases, we only need to multiply the weights with the vectors of the V bases. But if you want to represent a point in the U bases with respect to the V bases, we also need the reference point from the V basis itself. So we can write all this in a 4x4 matrix form, and because we do not have any coefficients over here and we do not need a fourth coefficient to represent a vector, we write zeros over here, and hence we get a 4x4 transformation matrix where the first three terms in the last column is zeros and whereas the last one is 1. So this way, having this type of a homogeneous coordinate form matrix that is 4x4, once we multiply a point with this matrix, we will end up with a point that will have a 1 at the as the last term, and if we multiply a vector with it, we will get a vector as output. So working with representations within the two coordinate frames, any point or vector has a representation of the form A is equal to alpha 1, alpha 2, alpha 3, alpha 4, or B is equal to beta 1, beta 2, beta 3, beta 4. If this representation is of a point, then alpha 4 and beta 4 will be equal to 1. If this representation is of a vector, alpha 4 and beta 4 will be equal to 0. The relationship of A is equal to M transpose B will still hold. If the matrix M transpose is a 4x4 matrix that specifies an affine transformation in homogeneous coordinates.